Hamming codes, a pillar of error. Correction in digital systems. Hamming codes are a family of linear error-correcting codes that were introduced by Richard Hamming in 1950. They are fundamental in the field of algebraic coding theory, known for their simplicity and efficiency in detecting and correcting single-bit errors. Hamming codes are widely used in computer memory, digital communication systems, and various error-sensitive applications to ensure data integrity. This essay provides an in-depth overview of Hamming codes, discussing their significance, functionality, and applications without involving complex mathematical equations. Basics of algebraic coding theory. Algebraic coding theory deals with designing codes that can detect and correct errors in digital data. The main objective is to maximize the reliability of data transmission while minimizing the redundancy, extra bits, added to the data for error detection and correction. In essence, coding theory strikes a balance between information efficiency and error resilience. Codes are constructed using algebraic structures such as polynomials and finite fields, which provide a systematic way to manage errors. Introduction to Hamming codes. Hamming codes are linear block codes, meaning they encode data in fixed-size blocks. Each Hamming code is characterized by its parameters, often denoted as n, k, where n is the total length of the encoded message, code word, and k is the length of the original data, message bits. The difference between n and k gives the number of parity bits, which are used to detect and correct errors. The main feature of Hamming codes is their ability to detect up to 2-bit errors and correct 1-bit errors within a code word. Functionality of Hamming codes. Hamming codes work by adding parity bits to the original data in a systematic way. These parity bits are placed at specific positions in the code word to ensure that the code can detect and correct errors effectively. The process involves the following steps. 1. Encoding. The original data bits are augmented with parity bits. The positions of these parity bits are carefully chosen to cover specific groups of data bits, enabling the code to detect and correct errors by examining the overall parity of each group. 2. Transmission. The encoded data, consisting of both data and parity bits, is transmitted over a communication channel or stored in memory. 3. Error detection and correction. When the received code word is retrieved, it may contain errors due to noise or other disturbances during transmission or storage. The receiver performs a check using the parity bits to determine if any errors have occurred. If errors are detected, the specific location of the error can be identified, and the erroneous bit can be corrected. Encoding process. During the encoding process, parity bits are strategically placed in the code word to cover certain groups of data bits. For instance, if the original data consists of 4 bits, k = 4, 3 parity bits are added to form a code word of length 7, n = 7. These parity bits are placed in positions that correspond to powers of 2, for example, positions 1, 2, and 4 in a 7-bit code word. Each parity bit covers a subset of the data bits, ensuring that the parity check equations are satisfied. If a parity check fails upon retrieval, it indicates the presence of an error. Decoding process. The decoding process involves detecting and correcting errors in the received code word. The receiver recalculates the parity bits and compares them with the received parity bits. If the parity check equations are not satisfied, the receiver identifies the bit position that caused the error and corrects it. This is done using a method called syndrome decoding, which helps pinpoint the exact location of the error based on the pattern of parity check failures. Applications of Hamming codes. Hamming codes are widely used in various fields due to their simplicity and effectiveness in error correction. Some notable applications include 1. Computer memory. Hamming codes are used in error-correcting memory, ECC, to protect data integrity in computer systems. ECC memory can detect and correct single-bit errors, ensuring reliable data storage and retrieval. 2. Digital communication. In digital communication systems, Hamming codes help maintain data integrity over noisy channels. They are used in modems, wireless communication, and other data transmission technologies to detect and correct errors caused by interference or signal degradation. 3. Storage devices. Hamming codes are employed in storage devices such as hard drives and solid-state drives, SSDs, to detect and correct errors during data read and write operations. This helps prevent data corruption and ensures reliable storage. 4. Satellite and space communications. Hamming codes are used in satellite and space communications to ensure the reliability of data transmitted over long distances. The harsh conditions of space can introduce errors, and Hamming codes help maintain the integrity of critical information. 5. Networking. In networking, Hamming codes are used in various protocols to detect and correct errors in data packets. This enhances the reliability of data transmission over network channels, ensuring accurate communication between devices. Advantages of Hamming codes. 1. Simplicity. Hamming codes are relatively simple to implement, making them suitable for a wide range of applications. The encoding and decoding processes are straightforward and can be efficiently executed using basic hardware or software. 2. Error correction capability. Hamming codes can detect up to 2-bit errors and correct single-bit errors, providing a robust mechanism for maintaining data integrity in error-prone environments. 3. Low redundancy. Compared to other error-correcting codes, Hamming codes add a relatively small number of redundancy bits, making them efficient in terms of data overhead. 4. Versatility. Hamming codes can be adapted to different block sizes and are applicable in various fields, from computer memory to digital communication and data storage. Challenges and limitations. Despite their advantages, Hamming codes also have certain limitations. 1. Limited error correction. Hamming codes can only correct single-bit errors and detect 2-bit errors. They are not suitable for applications requiring correction of multiple-bit errors or burst errors. 2. Fixed block size. Hamming codes are block codes with a fixed size, which may not be flexible enough for some applications that require variable length encoding. 3. Hardware complexity. While the mathematical operations involved are simple, implementing Hamming codes in hardware may require additional circuitry, which can be a constraint in resource-limited environments. Conclusion. Hamming codes are a cornerstone of algebraic coding theory, offering a practical and efficient solution for error detection and correction in digital systems. Their ability to correct single-bit errors and detect 2-bit errors makes them invaluable in applications where data integrity is crucial. Despite their limitations, Hamming codes continue to be widely used due to their simplicity, low redundancy, and versatility. As technology advances and the demand for reliable data transmission and storage grows, Hamming codes will remain an essential tool in ensuring data integrity and enhancing communication efficiency.